Whenever there is a decision that affects people, we really want it to be fair and not commit some injustice. Since these deep neural networks are often used to make some decisions that can affect people, so in some conditions they can even have a large impact, we need to be concerned about problems with bias in those decisions and also with the fairness, with the justice of those decisions. So we are going to look at in this lecture at these issues of bias in training deep neural networks and the ethical problems this may have. We're going to look at different sources of bias. This can be problems with sampling, with the population itself, with the way we set up the model, the features that we use, what we assume, and so on. And we are going to look at some methods to mitigate undesirable biases. But let's look at the idea of bias. So basically, bias is something that is not completely neutral. So everything that we assume about the model will create some bias. And in machine learning, we even have this term, inductive bias, which is a set of assumptions that we have that constrain the hypothesis and that are essential for allowing generalization. Because if we don't assume anything that can constrain the model we are creating, for example, using a linear classifier, using a network with some particular architecture, regularization, things like that, we cannot really generalize from the data that we have to new examples. So all learning systems need this kind of bias of having these assumptions and these restrictions to learn anything. Also, we have bias in the data itself, because in fact, bias is what we are trying to learn when we are learning about sets of examples. If everything was absolutely neutral and uncorrelated, there would be nothing to learn. It would be like everything being random noise, so we could not make sense of anything. So, for example, if you look at this picture, and if I asked you to label what is here, you would probably say that they are bananas, because we can recognize bananas and we have some assumptions about what bananas are from our experience and our knowledge of the correlations in this data set. But if I showed you this picture, this is a species, the blue banana from Java, that before ripening has this bluish color, then in this case we would probably label it as a blue banana, whereas in the other case we did not call them yellow bananas, because bananas are yellow by default, and if a blue banana comes around, then we specify that this is a blue banana. And this is the kind of things that we actually learn when we create these stereotypes, these prototypes, these ideas of what a category is, that reflect bias in the assumptions that we are making, in the way that we are thinking of those concepts. But this bias is crucial for learning, because if you make no assumption about the shape, the color, and the size of bananas, then you cannot have an idea of what a banana is, because an elephant could be a banana, the sea could be a banana, and so on. You need to have bias in order to learn something. So we cannot really say that we are going to throw away bias, remove bias, or something like that, because in that case we will not have information about the data and there is nothing that we can learn. So all of these stereotypes, all of these categories that we make in our minds to understand things, those are fundamental, even if they are always biased, because we need those things to generalize, to learn something. But there are cases where bias is not desirable. So the issue here is that there are some biases that we really do not want. For example, this review by the National Institute of Standards and Technology in the United States, they made a review of face recognition products, so basically neural networks for face recognition, and they found that the baseline error rate for white males is about 1 in 10,000. So this is the false matches between faces of different people that the system thought were the same people. But if they used, for example, images of American Indian women, the false positive rate increased by 68 times. And for American Indian men, was 47 times, and also for black women was about 10 times what it was for white men. So basically, these networks were trained on data sets that were strongly biased towards a kind of face, so light-colored people and mostly men. And then as we deviate from those faces, the network starts making a lot more mistakes. So here is an example where this can be very unfair, because if the police officers are using this system to try to match suspects to crime scene photos or things like that, then this very much higher rate of mistakes on some particular groups will result in terrible injustice in some cases. So there is good bias, all the regularities that we can use to learn, but there are instances of bias that we really cannot accept in our system because of the fairness consequences this has. This will create injustice and will create problems for people when we use this system. And this lecture will be about this kind of bad bias and the idea that we need to concern ourselves with these problems. So before we move on, let's consider this notion also of fairness, because now we have here an ethical notion, a normative notion that we need to set out clearly so that we know what we are looking for. So basically there are two intuitions here that we can consider. Our system will be fair if the results do not depend on certain features. There are specific features or specific characteristics of people that are even we are even forbidden from using them to discriminate people. The Constitution, for example, sets out that we cannot use sex, race, religious beliefs, sexual orientation, and so on, those kinds of protected characteristics to discriminate between people. And intuitively, we know that it would be wrong if, for example, our system for granting credit in the bank would give different results to exactly the same subject just by changing the race of the subject. So this would not be a fair outcome. So one of the intuitions we have is that not only we must omit such features from the input we give to our models, that part is pretty obvious. So if we cannot discriminate by sex or race, then we should not input as features into our model sex or race of the person. But we must also be careful of correlations, and when we are using unstructured data, this becomes harder. For example, if we are using photographs of the person as part of the input into our model, then it's very hard to guarantee that the model is not using sex, race, or country of origin or something like that to make its decisions. So in that case, we really must check if there are no correlations being used that would result in an unfair outcome, in the sense that the outcome is dependent on characteristics of the person that should not be used to make a decision. So if everything being equal and just changing, for example, the skin color, we get a different outcome, this is clearly an unfair system that we have created. Another important aspect of fairness is that our system works equally well on all groups. So imagine that you are creating an image classifier that identifies people that are the chief executive officer of important companies. So they had important companies and we want to see find them from the pictures. Suppose that we have a very good model that has 95% overall accuracy on the test set. There are only about 5% women among the CEOs of large companies. So if our model is simply rejecting all women as negative examples, it could still have a 95% accuracy overall because it gets right on the majority of CEOs that are men. But specifically for women CEOs, it could end up having 0% accuracy. And this would be the example of an unfair model. It's a model that is working well for some groups, but very badly for other groups. And if we are using it for everyone, then some groups will be treated unfairly by the outcome of those models. So this is an important problem when we have class imbalance in our data set. Because if you have a data set that is distributed somewhat like this, for example, you have 10% of class A, 30% of class B, and the rest of class C, then it's very likely that the model you train will be much more accurate on class C and less accurate on class A and B, because making mistakes on minority classes will weight less on the loss function than making mistakes on the majority of examples. But this can be an unfair result if our model is being used for something that will affect people, and if people are spread out differently in these categories, because this would be a model that would work very poorly for people of category A. For example, those face recognition algorithms in the case of people from minority ethnic groups that are underrepresented in the data set, and it would give unfair results because these people would be treated differently from people in different categories. What we would really like would be something like this. Even if the top accuracy would not be as good, or if we would sacrifice some average accuracy of our model, it would be preferable to have a model that would be have a similar performance on all of these groups and not discriminate against any of the groups. So this is another important intuition for fairness. It's not just that the model itself is discriminating in the sense of giving different results as a function of some feature, but also that the model cannot discriminate by having different performance on different groups, because this can be unfair if the model is used for something that has impact on the lives of people. Okay, so this is the notion of fairness that we are going on with. And a basic idea here that I think it's important to stress out is that this is increasingly important the more the method impacts on people, on society, and so on. So fairness in the network that you're using to sort your vacation photos is not really a significant problem. We don't need to worry about performing different in different groups and so forth. Fairness in advertising algorithms on Facebook that may influence how people vote and so on and affects millions of people, in that case, this becomes a very important problem, and we need some ways of checking how these algorithms are being used and how they perform in different groups, what kind of features they are using, and so on. So this is also important to bear in mind, that the issue of fairness is dependent, the relevance of this issue is also dependent on what we are using the model for. So in the discussion in this lecture, I'm going to assume that it will be models that are going to have some impact on people and not things that are trivial or irrelevant. So let's see where this bias can come from. Note that bias is precisely what we are learning, and so data must be biased in some way in order for us to learn. For example, this is the probability of classifying images of bridegrooms from the United States and Australia using a network trained on the ImageNet, and this is the probability of the network classifying these images as bridegrooms. So it's correctly classifying them. As you see, most of them have a large probability. This is the logarithm of the probability, so it's negative numbers, but over here close to 0, it's close to a probability of 1. So most of them are have a high score in the classification. But one problem is that ImageNet is biased for Western countries. So most of the photographs there come from Western countries. And so when we try to do the same thing with bridegrooms from Ethiopia or Pakistan in this example, then the errors become much higher. This is the distribution of the probability of correctly classifying or classifying this as a photo as a bridegroom, this kind of photo, and you see the distribution here with very low probabilities, because the network is not recognizing that this is a bridegroom, since this looks, the kind of clothing and the overall look is very different from what the network was trained because of this bias for Western countries. So one part of the bias that the network is learning is the bias that makes it a difference between a bridegroom and a boat and a banana and a dog and things like that, because those images are different, and that kind of statistical bias that we find in those in the differences between the different classes is being used by the network to learn classification. So bias must always be there. But there is one additional bias here that we would not like it to have, which is the network is only getting examples of one type of bridegroom with dressed in one particular way, and not getting enough examples of the ways people dress for weddings in different countries. And so it performs very poorly when we try to identify, for example, Pakistani grooms, and the network cannot recognize this kind of dress. So this is an example of bias that results from inadequate sampling in our data. If we are considering the population to be the population of the world, and we collect images only from some particular countries, then we have a sample that is not representative, and if we train our models in that sample, then things will go wrong. And if this is used for some kind of application that has impact on people, then it can lead to unfair results. Another more complex problem, or harder to solve, is when the universe itself is biased. So in this case, we could think that we can solve this by gathering photos from many countries and not just Western countries. And so we could enrich our data set and avoid this kind of bias that is coming from incorrect sampling. But suppose, for example, that we are looking at professions like nurses, construction workers, engineers, sociologists, and things like that, and there are very large gender imbalances in these professions. Some professions are much preferred by women and others by men, and so there is an imbalance there in genders in these professions. And we cannot solve this kind of bias. If we wanted our method, our algorithm, our deep model to perform equally well for all of these categories, male and female in all of these professions, we could not solve the problem of having these imbalances simply by using more representative sampling or random sampling or getting a larger sample, because the universe itself, the population we are sampling from, is biased in this particular way. So this requires other techniques, and we're going to see some examples, but it may happen that we need to mitigate or combat some bias that is not just the outcome of incorrect sampling, but it's really part of the universe that we are studying, and we want specifically to remove that bias from what the network is considering. Another source of bias can be the way we select features. For example, nearly all violent crime is committed by men. But of course, we can avoid using sex as a feature for predicting, for example, if someone will commit crimes again, or if they should go to jail for a longer time, or be denied parole, or something like that. Because sex is a protected characteristic, it's one of those that we cannot use to discriminate between people, and so we can try to put this out of explicit features. Nevertheless, the correlation remains in the data, because nearly all violent crime is committed by men. And so if we use features like height and weight and so on that are strongly correlated with sex, then once again the model can use those features as proxies for the protected characteristic and give us also unfair results, in the sense that we can have a network, for example, that gives some recommendation to the judge about how long a person must go to jail, and it will give different results if we just change the sex of the person or attributes closely correlated with the sex, because that would be what the network is learning as a shortcut for those recommendations. So we must be careful about the features we select because those may lead the model to use biases we do not want to be used. Note that, once again, I stress this, it's not possible to learn anything without biases. What we are doing is trying to rule out some of the biases that can be used as shortcuts and give unfair results. Another source of bias can be aggregation effects. We consider the average and disregard that different subgroups have different characteristics. One example is this hemoglobin variant, is a glycosylated variant of hemoglobin that has been bound to sugar, and this can be used as an indicator of high blood glucose levels. So we can use this to diagnose diabetes or pre-diabetes. And there are some levels that we can measure in healthy population and then decide on some threshold above which we have an indication that there are high glucose levels in the blood. However, when we look at this in more detail, we see that different ethnic groups have different levels, baseline levels of this kind of hemoglobin. So if we use an aggregate level for all the subjects, then we get unfair results because the same level will work fine for some ethnic groups, but it will not work for other ethnic groups. So we must disaggregate these groups and end up treating them differently, set different thresholds in order for the result to be fair and not depend on the ethnic group the patient belongs to. Okay, so let's see some ways we can mitigate undesirable bias in training deep neural networks. So one trivial source of bias to solve, at least in theory. In practice, then it may be harder, but it's trivial to understand how we can solve sampling problems. We just do better sampling and create a better data set that is representative of the universe we are considering. This is an example, this pilot parliament benchmark. This is still in work in progress, at least at the time of the paper I read, but it's trying to reduce the problem of face recognition data sets, which is to be strongly biased towards light-colored people, light-colored skin, and mostly men. So what the authors are doing is gathering photos from the parliament of different countries. So these are the members of parliament of different countries, and choosing representative samples of men and women, and also choosing different countries so that they get different types of faces, skin tones, and so on. So we have Finland, Iceland, we have Senegal, and South Africa, and so on. So if we gather people from different parts of the world and cover the range of different looks and skin types and gender and so forth, then we can have a proper sample of the universe of people, and hopefully algorithms trained with this kind of data will work better and not have those kinds of biases that make them perform poorly on some particular groups. But this is just one way of solving these problems, which is to get better data in the sense that is more representative of the population we are studying. If we cannot just get better data, or if the bias is in the population itself, so even if we try to sample carefully at random and so on, we can have still bias in our sample because the population itself is biased. Or if we don't really know what the biases can be, because note that in this case it's more or less obvious that if we want to train facial recognition networks, we need a sample that covers different skin tones, different ways of dressing, different genders, and so on, so that the network can look at all of these different patterns. But there are cases where we may not know exactly what the bias is there, what correlations are there in the data that may influence the way the algorithm learns. So one suggestion for this, and we're going to see two methods for doing this, is to change the probabilities with which we are going to sample from our data set when training the network. This is one way of solving these imbalances, but the question is, what are the probabilities we're going to assign to different examples? We could do this manually, and if we notice that we have 80% men and 20% women, we can change the probabilities of sampling for each mini batch, for example, so that each mini batch is created approximately half examples of men, half examples of women, and so we mitigate this problem in the data set when we train the network. But in many cases, we don't really know what the imbalances are there, because there are so many different combinations and possibilities. People may be taller or have larger noses or smaller ears or light eyes, brown hair, blonde hair, things like that, and we cannot really enumerate everything. So repair is one attempt to try to automate that, representation bias removal, in which we have a deep neural network classifier. And so we can think of a deep neural network classifier as being just a linear model at the end. You can think of the last layer where you have the softmax output is just a linear classifier that is being applied on the result of all the previous layers. And we can think of all the previous layers as having been trained to extract the right features from our data, so that this last layer, which is a linear classifier, can just tell us what class each example belongs to. So the idea of repair is to take these representations created by all the previous layers and retrain a linear classifier at the end with this cross entropy loss, so that we try to minimize the expected the expected minus logarithm of the probability of getting the class right given the features, where the features must first pass through all the layers of the network. So the actual features that are coming into our model, our linear classifier, is what the last layer of the network is seeing. So basically we take minus the average over all the data set of the sum of the logarithms of the probabilities. This is typically the cross entropy loss, where we take the logarithm for the loss function and then minimize that. But there is one additional thing that they want to cover, which is bias. And as we see, we saw bias is the whatever helps us classify, distinguish between different examples. So the lower the loss is for some particular model on some data set, this model would be the linear model just we're trying to adjust given the representation that our network produced. The lower this is, the higher the bias will be, because if we can really classify easily these examples, then there's some strong bias there distinguishing between the classes. This is precisely what we're learning. And we also normalize this by the entropy of all the classes, so that this is normalized between 0 and 1. But basically, this will be higher if the classes are all distributed evenly, and lower if we have things unbalanced in one class. Okay. But this is just to normalize this measure of bias for problems with different numbers of classes and different class distributions. The basic idea here is that the easier it is to classify the data set, the stronger the biases must be there. Note that we are not making a distinction between good bias and bad bias. This is not an evaluation of what should be removed. It's just the realization that bias will help us classify things correctly according to the loss function. And so this is how we can measure this, 1 minus the normalized loss function here. So the goal of repair is to find weights for all the examples that will change the probability of that example being chosen for training the network. So when we are getting examples from the data set, from the training set to train the network. Those with larger weights would have higher probability and come up more often, and those that have lower weights will have a lower probability and come up less often. So this changes the loss function by changing effectively the data set that we're using, because now we are not sampling uniformly from the data, and it's like we had a new data set where some examples appear more often than others. But this is basically the same expression, only we are now weighting each particular example by its weight, and this will be the effect it will have on the loss function in practice, because we pick it more often from the data. And also we can adjust the bias here by also weighting these different weights, but basically this would be the expression that we have for computing the overall entropy in the different classes. We have to consider the weights for each class, for each example relative to the total weights on the class, and then normalize everything by the sum of the weights. But this is basically the same thing where we are weighting differently each example, and the same thing here for the loss function where we are giving different weights to the examples. But now comes the trick here, which is to adjust the parameters of this linear classifier that is using the representation the deep neural network generated, in order to minimize the loss function with respect to the parameters. So we are going to learn to classify as well as possible the examples using the representation the deep neural network created. But then we're also going to minimize the bias here, which means that this will have to increase in order for the bias to decrease. But we're going to do this with respect to the vector of all these weights we are giving to the examples. So the intuition here is that everything that facilitates classification because of the way the data is distributed, because this example appears more often and the other appears less often, will tend to be eliminated as we are minimizing the bias with respect to the weights. But we still are looking to doing that with the best possible linear classifier that we can create with the features that are represented there. So everything that is not just connected to how the data is distributed can still be used for classification. All of those biases we use. We are just eliminating the biases that facilitate classification and are dependent on the distribution of the examples in our data set. So this is how repair can work, to give you different probabilities of sampling different examples in order to eliminate those bias coming from different distributions of different examples in our data set. And this can help identify combinations of features that we would not easily find, because remember that we are using here just the terminal part of the network, taking advantage of all the representations the network used. And once we have a more balanced data set, at least in this for this criteria, then we can retrain the network using those probabilities. The way this is done, the minimization of the loss function with respect to the parameters and then minimization of the bias with respect to the weights, is similar to what we saw with the generative adversarial networks. Basically, we alternate training on one and the other, and we keep doing that until we reach convergence. Another approach is to use variational autoencoders. Remember, we talked a bit about this. Variational autoencoders provide a latent representation of our data with parameters for probabilities distributions, and also they are good at untangling different components of the features of our data in that manifold, in that latent representation that the autoencoder is creating. So the architecture proposed by the authors here is to have this classification network. So we have the input, this part of the network that also works as an encoder has some outputs that will be used to classify each example. So this part here in blue is just a classification network. But the encoder also has a set of outputs that will consist of the latent space representation. So remember, from variational autoencoders, these will be the parameters of the distributions, typically normal distributions, so mean and standard deviation, for the representation here, from which then are sampled examples into the decoder, and we have a reconstruction error by comparing to the input. So this part here is trained in an unsupervised manner. This is an autoencoder, while this part here is trained in a supervised manner because it's classifying the examples. And the overall loss function is a weighted sum of the cross-entropy error here for the classification, the Kullback-Leibler divergence for the latent space representation in the variational autoencoder, and the reconstruction error that we have here. So this is all trained together in adding with different weights that can be calibrated these different components of the loss function. There is one detail here in that we can block the gradients, so stop learning, whenever we have examples from classes that we do not want to debias. So you can select that we only want to apply this debiasing method to some classes and not others, and we can filter this so that the autoencoder ignores the other classes that we do not want to debias. But this is just a detail so that we can fine-tune the classes we want to debias. The important thing here is that this latent space representation gives us points in this manifold for the different probabilities, the different parameters of the probability distribution in the manifold that is being created by the variational autoencoder. So the variational autoencoder is creating a representation that captures the important aspects in our data set. So now what the authors do is to compute histograms of different regions of the distribution over this latent space, so that they can find that there are some images, for example, this kind of images that appear here, appear in a very dense region of the latent space. There are many examples that fall in that region of the latent space. And this is more or less the standard of these kinds of photographs, where the person is looking straight ahead, has light skin, it's a young person, and so on. And most of the photographs end up being like this. And so all of these get projected near the same point in the latent space, and we have a large bar on the histogram when we look at that point of the latent space. Then there are other kinds of images that we have with different illumination, different poses, people have different ages, skin colors, and so on, and these fall into less occupied regions of the manifold of the latent space the autoencoder has built. So what the algorithm does is to assign a sampling probability of these examples using the inverse of the density in the manifold region. There are some parameters that we can adjust, a debiasing weight there, but the idea is this, that if images fall into less tightly packed or less dense regions of the manifold representation, of that manifold of the latent space representation, then they get a higher probability of being selected for training. And those that fall into places in the manifold that have lots of examples that are very tightly packed, they have a lower probability of being sampled. So this is fed back here and adjusts the sampling probability of the data, so that when we create the next mini batch, we have different probabilities of selecting this data. And this can be done continuously, updating regularly these probabilities, and retrain and keep training the network. So this will allow us to train the classifier using a distribution of data that tends to be more homogeneous in what the autoencoder considers to be a proper representation of the structure of the data. Because note that there are lots of features here that we can see. We can see, for example, that the people in this more crowded subset are all light-skinned, all attractive, all young, but this is not something that we can easily tell the network. We cannot just specify that on the images because we cannot easily control this. But the latent space representation can identify these kinds of common features of these images, because the variational autoencoder is learning the structure of the data and how to represent it properly. So this is the important part here, is that we are using the agglomeration or the accumulation in different parts of the latent space representation to decide to give a lower probability to that kind of input, to those inputs, so that we spread out things more uniformly in the latent space. And this captures all the different biases that the distribution of our data can have. And now the classifier will tend to learn according to things that are actually correlated to the features of the images, and not just an artifact of the improper distribution of the data in the training set. Okay, so to conclude, we saw that bias is good, but it's also bad, because bias is fundamental to learning. All the correlations that we find that allow us to make a prediction based on the features, those are biases. We need to find those biases in order to learn something. But whenever those correlations either arise from mistakes, from improper representation of our data, or can lead to unfair results, either because the output of the model depends on characteristics that should not have influence on the outcome, or that it's performing differently in different groups of subjects. So whenever this is important for people and results in this kind of unfairness, we need to identify these biases. And we saw these methods for trying to mitigate this, but this is part of a broader set of practices that you must take. Consider how the model will be applied, what it will be used for, and what impact it can have on people. So that gives you an idea of how important fairness considerations are in each particular case. We must be aware of anything that can be used by the model to discriminate based on those characteristics that should not be used. This is not only explicitly avoiding using those characteristics like sexual orientation or religion or things like that, but also avoiding or being careful of anything that can correlate to those attributes, and then give a shortcut to the method to say, okay, if this person is Muslim, then we reach this conclusion because that works most of the time. We cannot accept those kinds of shortcuts in models that will have impact on the life of people. We also must be critical of the data sets that we are using, not only because the sampling may be incorrect, so we have something that is not representative of the population we are interested in, but also because the population itself may have biases that we want to avoid or to mitigate. So we need to evaluate the performance of our model in different groups whenever fairness is a relevant issue, because overall accuracy, for example, may be hiding some unfair results because our model is not working properly on some minority groups. And if things are really important and we have questions, we should try to mitigate by actively reducing biases. And the examples I gave to you are basically the fundamental idea is that we're going to try to eliminate all the imbalances in our data set that are helping the classifier. So if the classifier can increase performance just because there are more examples of one type than the other, then we try to break that possibility and reshape the data set, the probabilities of drawing examples, to minimize those kinds of shortcuts and prevent the classifier from taking advantage of those changes in distribution. So it will have to focus on the actual attributes on the examples and not on the fact that there are 90% of these and only 10% of the other. So this is the general idea, but basically I think that these problems of bias and fairness is mostly a question of being aware of the problem and really thinking about what can be going wrong in your model and the process of training it that could have relevance in these aspects. Okay, so to sum up, we have to remember that the problem of bias and fairness is fundamentally an ethical problem. There are machine learning methods that we can use to try to solve that problem, and it's something that is applied in the case of deep learning whenever we need to use this to have some impact on people. But bias is always present, and it's what the model uses to learn. The ethical issue is that some biases are not acceptable, and we need to remove those and use only other correlations. So sources of bias that you need to take care to consider are possibilities that sampling is not representative. Even if it is, the population may not be conducive to having a fair outcome, and we need to change the sampling. Other assumptions that we are making, the features we are selecting, the aggregation we are using, and so on. And also these methods we cover to try to mitigate undesirable biases. Okay, so now we have some time left for questions, I think mostly about the assignment. So I'm going to log into Zoom and we'll meet at the session. See you soon.